Good day, folks. I'd like to talk to you today about something else I noticed the quantum power cells with the solid state electrolyte is good for here. So here it is, still running the LED here pretty brightly. It's been doing that, I guess, for a few months now. And what's interesting is it's a pure electrostatic effect. There is zero electron flow other through the load. So to show you that, I'm going to disconnect one side of the LED here. And I got the meter set up to beep mode to show you that when I touch both, just gonna snap this one in there. Just bear with me, one hand. Just gonna put the clip here. Come on. There. Wow, okay. All right, we got it. And this one here, no beep, see? Let's bring the resistance up to the highest value. Let's see if we could even measure super high resistance. So no. Touching it now. Nothing at all. So no electron path whatsoever, okay? But because of the electrostatic displacement, as I've explained in other videos, when we connect a DC load like the LED, it works, see? Now, this got me thinking, folks, about regular power cells, DC series configurations, you know, when you connect plus and minus, and stack the batteries up, identical batteries usually, and you can combine their voltage, but they stay at the same current of one battery. That's the series configuration. But they have to be perfectly symmetric, because what happens is if one is any lower in a different state, it might affect the whole chain, the current distribution. So in traditional setups, it's very important to keep the same batteries in series. But what's interesting is if you were to draw a schematic of a simple series cell through a lamp, it would be a closed loop. And there's an electron flow, you see, even through a battery here. You can't do this very long on the battery, but if I were to measure at the lowest here, 2 ohms, and I measure the 9-volt battery, this is like a half-dead battery, by the way. So I measure that, I get a little over 1 ohm. Oops. Let's see if I can get it there. It's very hard with one hand. See, 0.6 ohms roughly. So it's very low basically. It's got some resistance, but enough to very low to create a good electron path. So you got your closed loop, as Tom Bearden talks about, okay? And that's what drains your batteries. You got that closed electron loop. And Tom Bearden talks about keeping the loop open and how the battery itself is that dipole of energy. If you don't close the loop, and it will forever keep giving you that pure potential if you don't close the loop. So that got me thinking, you know, these cells here are not operating traditionally because they don't have an electron flow. So what happens is if I disconnect the LED here, and this is the negative side here, and I plug it to the plus side here, and put this battery here in series, and I measure the voltage, I'm going to put the voltage here. This is very interesting because now when I put the meter on, there's no closed electron loop through the battery, yet I'm still going to measure a higher voltage. So I'm just going to go through the battery. It's going to be hard to do this with one hand here, bear with me. Okay. I need a stand for this. Okay, carefully. Come on. Alright. I just want to show you folks, when you put the battery in series, I'm measuring a voltage with no closed loop through the battery. Now I thought that's pretty interesting. It's the dead battery, so it's gonna, but it's still pretty good because I'm getting over 9 volts because it's accumulating, and I'm shaking a lot here. But if I can get it, it's over 8 volts, like even 9 point something, but I'm shaking a lot here. So then I thought, okay, plug the LED directly through the battery like this, and look how much brighter it is now. And what's cool and very interesting with this is there is no closed, if I could just get it to hold there. Ugh. Okay, come on, be nice to me. When I'm doing this alone, no problem. When I wanna, there we go. So super bright now with the addition of the voltage. Now, if this was a normal cell series configuration, the two of them would share whichever the lowest one would be. That's the current that would be outputting through the battery. But what's going on here is there's no direct electron flow. So this is actually acting as an ion valve, and we're separating the electrostatic from the battery. And we're getting a pure potential difference, and this is the pure electrostatic going through the load. So this is displacement power, not real current. There's no closed loop, and we're operating this exactly now in the Tom Bearden specifications of operating the loop, keeping the dipole open in the battery. And thanks to the cell, now some may argue, well, it's capacitive and it's going through that way. Okay, yes, there is some capacitive element to this, but we're running a DC system. So in a series configuration, adding a capacitor in the loop is actually a DC blocking phenomenon. So there wouldn't be this continuous loop unless you had a circuit mechanism that keeps switching and dumping that capacitive element. So, you know, that's not it. For this effect, it's purely potential difference. And if you're following me, this will run for a very, very long time because we're not closing the loop. The load is appearing right at the LED. It's a non-traditional electric flow here that we're dealing with. So basically, if you follow me and you were to maybe find, 99 volt batteries, put them in series and connect them through the cell, you'd be able to easily charge your big capacitors at 80 volts and dump them through your capacitive dump. And this will charge big 12 volt batteries and will keep running for a very, very long time because there's no electrical closed electron loop here. So you're just stacking up on the pure potential difference and the electrostatic coupling through the cell, and it acts as a ion valve. We're separating the electron from the ion flows, and the cells takes care of creating that potential difference and separating the charges. So you do get a flow, but it's not real current, it's displacement current. And the loop remains open electrically. So this is really neat. I love watching it glow like this because if you understand the mechanisms behind this, this is exactly what Tom Bearden was saying. You can't normally run a battery in an open loop system, but with the help of what this is doing with the solid state electrolyte and the ion and electrostatic, it's additionally creating a potential difference between each side, essentially, of the LED. So yes, folks, you can do a lot with electrostatic if you know how to handle it properly. So I just thought I'd share you this because it's very interesting and a very efficient way to basically use your batteries. And yes, of course, you got to remember, because there's a little bit of a capacitive effect when you initially, when you get a momentary flow, but that's just when there's a change of current state in the system. So if you keep messing around with it and pulsing it manually, then you'll eventually keep pumping the battery. But just keeping it as is, as long as there's no fluctuations, we're good. So I just want to put that out there. Very good information. Literally operating the LED in an open loop There's no electrical closed loop. I showed you the resistance. There's no beep. There's no high resistance even measurable on the meter. But the power cell, the battery does, and it's pretty low. So it's basically combining the potential difference of the cell with its own. But because it's on one side, you see, on one side of the cell and on the other, it's part of the series configuration. So the solid state power cell is what actually breaks the electron flow across the loop here. It's literally like running the circuit as an open. There's no direct electron flow. Yet we still have, and it actually contributes. So it's all in how we design our systems and manipulate our interactions. And Tom Bearden gave us a good hint here. And I hope this is good information, and I'm going to wrap it up and have yourselves all a great day.